Today we're going to see this topic that you see on the screen right now, generating models of mechanical systems. The idea is we have a little system in there and we need to find a systematic way of generating the bond graph model of the system. So what I'm going to be doing is we're going to outline some steps on how to do it, and if we follow these steps we should be able to generate a model of mechanical systems of this magnitude or more complex, because the steps would be the same. So let's take a look at the first step that I'm going to write down in here. Okay, we're going to say step number 1. I'm going to say represent each velocity in the system with a one junction. One junction is the one junctions are the ones that are used for common velocity junctions. So what I would do is in here you see you have a common velocity junction in here because the let's see for common velocity junction because the this is the mass, right here on this. On this side you have this force, and on this other side you have the spring and the damper. So in here you have the case where your velocity junctions are the ones for the mass, and you have also a velocity junction for the wall. Okay, so what we're going to do, true to what I just said, is I'm going to put a one junction here to indicate the velocity of the wall. I'm going to put another one junction here to indicate the velocity of, x dot, really. And so that's the first step that we are taking, is to do this, to use a one junction for each velocity here. So now what we need to do is we need to put a step number 2. So this in here, step number 2, use a one junction to represent each distinct velocity. Okay, very good. We have done just that. And then step number 3, we're going to say attach the elements that experience that velocity. So the experience will say each velocity. Okay, so in here we go. You see you have it on the right hand side. You have this force in here. So we need to represent that. We need to represent the inertia element. And we need to represent these forces that are acting on the mass. So in this case, the first thing we have to do is to put the sources. I'm just going to use red. So in here, we're going to put source of effort. Yeah, so this would be the value of this F, right? We also know that in here we have SF, which would be the velocity of the wall equal to 0. Saying it doesn't move. Now on this side, on the right hand side, over here, we represent that as we need to represent the inertia, the mass as an inertia element. What I'm trying to say. So this is going to be like this with value m. Okay, and then that's step number 3. Make sure that we consider all the elements that experience each velocity. And then in here, in number 4, this you're gonna say use zero junctions to represent the difference in velocities. Okay, and then five, you can say use you could say no, not the word use. The word represent is better. Represent the elements that see or that experience represent the elements that experience those velocity differences. Okay, very good. So in here, the only thing we have is that here on this Okay, here's what I'm trying to say. You have this element that sees the difference between this velocity and this one. So this would be the velocity x dot, and so this difference is represented by another one which means x dot minus velocity of the wall. And that difference is seen by both of these, by the C element, which is 1 over C element. It has a number, you know. The I element is over here, and in here you have this. So there's another resistor, another resistive element in there. So this is how you generate the the bond graph model that you can put into CAMG. Now, you could use this model as is, not a problem. But you could also simplify it. You could simplify it to obtain the form that is in your slides on the web page. So what we need to do is simplify this if we want, because the velocity of the wall is 0. So it is because this graph has the velocity 0 here, so we could suppress this. See, this part in here is as if it doesn't exist, because the velocity of this side is 0. It's almost like no. So if that's true, then it follows that, let's just go one step of the reduce graph, so you can see how we are going to reduce it farther down. Let me just switch colors here. This means that the part that you see in there, this is gone. So what you are left is 0, and this is a 1. And you have the I element over here, you have the AC element over here, the source. The rest on the left is gone, and this is a 1, and with the C and the R element. This is all we have. But we need to consider, you could say, but remember that if you have this, or you have it the other way, doesn't matter which way it goes, like in this case. In this case, you see. And that means that this is also the same as this. So you could actually suppress it even, simplify it even further down. because now you see if you have this as E1 and F1 to an F2 by the definition of 1, F1 is equal to F sub 2. Okay, so if you have this, you can say doing the simplification, you can say simplifying simplifying simplifying, you'll have that this is a 1. C element, and of course in here you also have the I element. So this is the way we have simplified the model for this. Okay, so what I would like to do is to go over the block diagram of this. So in conclusion, here we have technically produced the entire bond graph model for this. Yeah, let me just make it a little pretty here. Perhaps this is a there we go. You can put the bond numbers in there if you want, but the ChemG will do it for you. So this is the way we generate the block diagram, I mean the bond graph model. So to complete, you may say in here on the last step, you say 6, I would say verify causal marks and power flow. So you always need to check that. So in here, we could say look, because we know how the elements are connected, we know for sure that this is producing a voltage over here. Okay, and then you have, if this is the flow into the one junction, all the others have to be like this. And the efforts are the same, and they're equal to, let's see, this one right here. So you could enter this into the ChemG software, or we could just begin generating the block diagram model. But my emphasis here on this short video was to illustrate how you actually generate the bond graph model of a mechanical system. What I'm trying to say is you could have left it in here. There's nothing wrong with this graph, but I did the simplification because the textbook also does it, and I wanted you to see where it came from. So right now on the next segment, we need to generate the block diagram for this. So let me just, we'll break it in here and